last talk of this pre-lunch session by Dr. Anjan Ray on CSIR revision in petrochemicals. And after that we will have discussion and we will take questions from the audience.
Good afternoon, Professor C.N.R. Rao, Professor Sood, Dr. Mande, past, present and incoming members of the INSA Council, ladies and gentlemen. As the last speaker and being acutely aware of the time constraints, I'm going to keep my talk relatively simple, and I'm going to talk about something that Professor C.N.R. Rao mentioned over 25 years ago. He talked of energy independence. And today I will take that a step forward and I will talk about carbon independence in the context of fuels, chemicals, and petrochemicals. We are sitting here on the coast of India at Goa, and we should be acutely aware that in my childhood, the animals that were there, 60% of those species are not there anymore, and marine populations, freshwater as well as marine, are hugely hit. And a lot of this can be attributed, whether we agree to accept it or not, to human activity, to anthropogenic interventions. A major part of anthropogenic intervention comes in the form of energy usage. For all our activities, we use energy. For a majority of those activities, we tend to use carbon. If you look at the primary energy mix of the world, and we look at the primary energy mix of India, and we look at the forecasts, we can be fairly confident, based on studies by various knowledgeable and expert organizations, that our dependence on fossil fuels is not changing fast enough to make a meaningful slowdown in that impact that we saw in the first round. In India, you can see that something like 92% of our primary energy is still coming from fossil fuels. I'm not even going deep into the aspects of climate change and carbon dioxide and GHG emissions, but we are all aware. So if we just look at the oil and gas market and we think for a moment as to where all this carbon is coming from or going, whether we take oil or natural gas or whether we can take coal, all of those eventually end up either in some fuels, which are down here, or some kind of chemical, which is mostly out here, and then some large bulk chemicals. Sadly enough, in India, the top 50 bulk chemicals, majority of those are still imported. So we are right now looking at a country where we are dependent on a diet of imported carbon atoms. How many carbon atoms do we actually import? A very simple sum, because most of the carbon atoms that we import are in these three blocks. That's about 350 million tons. And we use them both for energy and for chemicals. So we can really do only two things. If we want to become carbon independent in a true sense, we must either reduce the requirement from the demand side, either the energy requirement itself, and we've seen energy efficiency highlighted in a number of the talks, or we must reduce the carbon requirement. Again, a lot of activity in this area in this country. Or we must focus, I would say obsessively, on finding domestic carbon to replace our fuel carbon imports. And we must do this, all of this, whether it's non-carbon energy or domestic carbon replacement, we must do it with a conscious measurement of the overall GHG impact. We should not increase the greenhouse gas emissions in trying to get from A to B. So how much carbon do we have actually in India? When we first sat down to do this accounting about 3 years ago, we were amazed to find that particularly the wet wastes and the high GHG areas, as well as a lot of our urban wastes, a lot of our agri wastes, they add up to over 500 million tons of waste carbon. So all the carbon we ever needed and that we're importing is actually available within our borders. So maybe we set our petrochemicals vision, in fact our fuel and chemicals vision, to deploy domestic carbon in an efficient manner. How do we do that? All of these, I have taken some very clear These represent 98% of the carbon used in the country. 98%. And for every one of them, replacement technology, replacement chemistry is known. What is missing is scalable adoption. Everywhere almost you see issues like scalable infrastructure, economic value. So it's not as if these things haven't been worked upon. It's that they have not been institutionalized. And the same was true with solar 20 years ago. The same was true with mobile phones 30 years ago. And we know that it's everywhere now. So there's no reason why we cannot do this. The key is to focus not on technology alone. The key is to focus on an efficient, effective supply chain end to end. So I'm just going to make it very simple. We have had work done in this all over CSIR, but from my lab, because we know this well, and we have some very focused interventions, I'm going to show these. But let's not forget that we are building this on the back of tremendous CSIR knowledge base. For example, NCL licensed one of the world's largest biodiesel plants. It's currently operating in the US for the last 5 years. IICT has just recently built a new plant for hydrogen hydrate. There are technologies that are all over the country in energy efficiency from Needy's bookstore. So we'll just take a few examples from IIT, very recent ones. Many of these are on display in the stall outside. I would strongly encourage you to go look at them. But let me start with supply side solutions. This, Dr. Jadhav mentioned, this is a biojet fuel. And a biojet fuel is nothing but a form of kerosene. It is nothing but a feedstock for detergents. I mean, what I can do to make biojet fuel, I can also do to make kerosene or detergents. I can also use this to make lubricants. So the right carbon chain length, 10 to 15 carbons roughly. And we used vegetable oils, not necessarily the infamous Jatropha, but over 400 oils available in this country can be made into this biojet in the same plant with the same catalyst with minor tweaks in process conditions. This is one of our pride and joys. It is on display right now outside. We will make biodiesel in front of you in 30 minutes without heating, without stirring. And this is something that can go to the village level, literally community. We make it from used cooking oil. We are collecting in Dehradun, we expect to collect 1 lakh liters of used cooking oil this year because India imports a lot of cooking oil. And what we are saying is that if 10% of our villagers can make 1 barrel a day, for which the prototype unit is already ready, we have the equivalent of a Mathura refinery production of diesel. It's a very simple process. It uses a science concept of thermodynamic neutrality. I'm starting with an ester and an alcohol. I'm going to an ester and an alcohol. All I need is an activation energy. That activation energy, if I can produce through a very large number of small particles, essentially through a microemulsion, I can go directly from here, the catalyst and the oil, form the microemulsion inside this, and the microemulsion itself, because the two are immiscible, will separate. This requires virtually no energy. So, compared to how much energy we take to make diesel, we can do this now at a fraction of that energy, maybe with an 80% saving in carbon footprint and net energy. These are the kind of questions we have needed to ask. And we've shied away from these because it is very challenging for a scientist to imagine the future vision. But the truth is, if we take a preborn oil seed and we can't foresee the yield and we can't foresee the uncertainties, we will never have a project that makes scale. Similarly with algae, it's a simple answer. We just recently reviewed a project that to get 100 tons of oil per day, you need a 20 into 100, 2,000 acre coastal lagoon to get just 100 tons of oil a day. So the question is then, if these are not yet delivered, how do I get enough lipids for the vision that I just explained? So first example, I said 400 different trees. We have an absolutely stunning solution from IHBT Palampur, which we think we can scale in the next 3 years. And this becomes extremely efficient because the tree that they've identified, Sapium seminiferum, gives not only oil but high value wax. And the wax can cross-subsidize the oil in almost all waters. We can also take feedstocks that are lying around, whether it's municipal waste or whether it's cosmetics that are discarded at the end of their life, or whether it's fruit peel, and we can feed it to an yeast, which is oleaginous. And what would take normally 6 months through a microbial system, we can do in 80 hours with our yeast in a fermenter, currently running at a 750 liter scale. And we are getting very close to the theoretical yields, 17 to 20 grams of theoretical yield. We are beginning to hit about close to that, but using a C5 sugar, not a C6. And C5 sugars are currently surplus in India. Similarly, with around waste plastics, it's very easy to convert that to petrochemicals. We have an operating plant of 1 ton per day now in IIP. We take 5% of their waste plastics, and in a swing plant, by changing the catalyst, we can make diesel, we can make petrol, or we can make LPG. We can also make kerosene, from where we can make detergents. From gasoline, we can go to naphtha, and we can make selectively VTX. All of these are now within our grasp. We're pleased to say that we just signed an agreement with Delhi Development Authority to take this to Delhi Municipal Corporation use of the plastic waste in Delhi. The product we get here is a Euro 6 diesel. The byproduct is LPG, which is used for firing the plant. Similarly, inside the city of Pune, in their Kachra dump and cartridge, we have a biogas upgradation plant to make either compressed natural gas or piped natural gas. And this is a unique pressure cum vacuum swing absorption system that we've designed. We work with NCL for the pre-treatment to make the kitchen waste even more amenable and cost effective. In our country, we have a lot of small fields where we flare the gas. The gas has no value. That gas can be captured, and in a 3D printed reactor, in a program where we partnered with RMIT in Australia, and where NCL has developed some excellent catalysts, we can actually go on site at a plant to make methanol and capture all the stranded gas. On the demand side, similarly with the piped natural gas, we have a special burner on display over here. As the cities go into PNG, piped natural gas, we must recognize that the vapor density of LPG, which we've used all our lives, is much higher than air. It settles. Whereas piped natural gas is lighter than air, it goes up. Simply by redesigning the burner, keeping this in mind, and looking at the flow behavior of the gas coming out of an LPG cylinder, where the pressure is reducing over time, versus a pipeline where it's constant over time, we are able to redesign a burner which gives us 25% efficiency improvement. We ran this burner for 6 months in the pantry of the petroleum minister inside his ministry, and it delivered the improvement that we promised. We hope to do 1 crore burners in 3 years from now. Similarly, at the informal end, energy efficiency of Jaggery units, gold is made all over the country. These are the traditional units. This is the unit made with our technology. It simply changes the heat flow so the Jaggery is uniform, and the combustion of the gas that is used is essentially complete. In all of these, we are looking at energy management, and this is one of our new and exciting programs where we know, and the petrochemicals industry is very nervous of what's happening in the EV world. But at the same time, if you're going to be scrapping vehicles and putting new vehicles into EV, we are really going to be spending a lot of energy in scrapping that vehicle. First, urban land to keep it. Second, energy to melt it. 3, reshaping it. Instead, we simply have taken out the engines, and with the help of Simeri and Sikri, we are converting these to electric cars. 2 cars are operating on our campus. They have been replaced with induction motors, and we have enough space in the manifold once we've taken out the fuel tank and other things to fit either a battery and or a supercapacitor and or a fuel cell, essentially creating a living car with an infinite life. We just keep changing panels and components. This is all I had, but going back to sustainability, we do measure this on a running basis. In our campus, we measure the biodiversity of what the work we are doing is having in our neighboring ecosystem. And we must remember all these sustainability parameters have to be met in order for us to feel good about what we do. So this is our campus. We invite you all to come visit. We expect this count to be up this year to over 75, and we expect this count to cross 100 this year. Thank you for your attention.